In the darkening months of 1942, as Allied bombs began to rain down upon German cities with increasing frequency, Adolf Hitler found himself confronting a reality that had once seemed impossible. Germany was losing the initiative in the war. The Führer, whose military campaigns had swept across Europe with unprecedented speed and efficiency, now faced the relentless pressure of Allied air superiority over the Reich's industrial heartland. It was during this period of mounting desperation that a concept emerged from the mind of a brilliant but ambitious ballistics engineer named August Coenders, a proposal so audacious that it would captivate Hitler's imagination and ultimately lead to one of the most extraordinary engineering failures in military history. Coenders approached the Nazi leadership with a vision that seemed to spring from the pages of science fiction, a massive artillery piece capable of firing shells across the English Channel from the coast of occupied France directly into the heart of London. This was not merely another conventional gun, but a revolutionary weapons system that would employ what he termed the multi-charge principle, a concept that would theoretically allow a single barrel to propel projectiles over distances that had never before been achieved in the history of artillery warfare. The engineer's calculations suggested that such a weapon could deliver devastating salvos upon the British capital with a frequency and intensity that would break the will of the English people and force them to sue for peace. The technical specifications that Coenders presented to Hitler were breathtaking in their ambition. The proposed cannon would feature a smooth-bore barrel extending over 130 meters in length, angled at precisely 50 degrees to achieve optimal trajectory toward London. Unlike conventional artillery pieces that relied on a single massive charge to propel their projectiles, this revolutionary design would employ an initial breech charge followed by 32 additional subsidiary charges positioned along the length of the barrel. Each of these secondary charges would be electrically detonated in perfect sequence as the projectile passed, providing successive boosts that would accelerate the shell to an unprecedented muzzle velocity of approximately 1,550 meters per second. The psychological appeal of Coenders' proposal to Hitler cannot be overstated. Here was a weapon that promised not merely military advantage, but the restoration of German technological supremacy and the delivery of the vengeance that the Nazi ideology demanded. The Führer envisioned batteries of these superguns positioned along the French coast, each capable of firing massive 97-kilogram finned shells across the Channel at a rate that would saturate London with explosives. According to Coenders' optimistic projections, 50 such guns operating in coordinated batteries could launch 3,000 rounds per day, creating a zone of destruction covering 15 square miles of the British capital. The weapon system that would eventually be designated as the Vergeltungswaffe 3, or V3, represented far more than a simple artillery piece. It embodied Hitler's desperate hope for a technological miracle that could reverse the tide of war. The codename Hochdruckpumpe, or high-pressure pump, was chosen to conceal the true nature of the project from Allied intelligence, while internally, German engineers sometimes referred to it as the Tausendfüßler, or centipede, a reference to the multiple subsidiary charges that extended along the barrel like the legs of the multi-legged creature. As 1942 drew to a close and the project gained momentum within the highest echelons of the Nazi war machine, few could have predicted that this ambitious venture would ultimately become a monument to the limitations of even the most advanced engineering when confronted with the practical realities of modern warfare. The stage was now set for one of the most extraordinary construction projects of the Second World War, an endeavor that would consume vast resources, employ thousands of workers, and ultimately achieve nothing more than providing future historians with a fascinating example of how technological ambition can be overwhelmed by the inexorable forces of strategic reality. The selection of Mimoyekes as the site for Hitler's supergun project represented a masterpiece of strategic planning that took into account numerous factors essential for such an ambitious undertaking. Located in the Pas-de-Calais region of northern France, approximately 12 miles southwest of Calais and 150 kilometers from London, this seemingly unremarkable chalk hill possessed characteristics that made it ideal for concealing and protecting what would become one of the most extraordinary military installations ever conceived. The geological composition of the site proved particularly advantageous, as the solid chalk formation extended to a depth of more than 100 meters, providing both the stability necessary for the massive gun installations and the natural protection that would be required to withstand the inevitable Allied bombing campaigns. Albert Speer, Hitler's Minister of Armaments and War Production, assumed responsibility for transforming Coender's theoretical design into operational reality. The project fell under the auspices of Organisation Todt, the Nazi engineering and construction organization that had already demonstrated its capabilities in building the Atlantic Wall fortifications along the European coast. The scale of the construction project that began to take shape at Mimoieques in June 1943 was staggering in its complexity and ambition, requiring the excavation of millions of cubic meters of chalk and the creation of a subterranean fortress that would extend more than 100 meters beneath the surface of the French countryside. The workforce that descended upon Mimoieques represented a microcosm of Nazi-occupied Europe, comprising skilled German engineers and miners from the Ruhr region, alongside hundreds of forced laborers drawn from across the occupied territories. French, Italian, Russian and Polish workers found themselves conscripted into this massive undertaking, laboring in 12-hour shifts under the supervision of German overseers who drove them relentlessly to meet the ambitious construction deadlines. The human cost of this project would prove to be substantial, as workers toiled in dangerous conditions deep beneath the earth, constantly threatened by cave-ins, flooding, and the ever-present risk of Allied bombing attacks. The architectural plan for the Mimoieques complex called for the construction of two identical bunker systems, positioned 3,000 feet apart, each designed to house multiple V3 installations. The engineering specifications required the excavation of 10 inclined weapons chambers, each extending 138 meters in length and angled at precisely 50 degrees to achieve the optimal trajectory for shells targeted at London. Each chamber would accommodate 5 individual gun barrels, creating a total battery of 50 V3 cannons capable of delivering the massive bombardment that Hitler envisioned. The construction also included 2 railway tunnels extending 650 meters in length and positioned 100 meters underground, designed to facilitate the delivery of ammunition and supplies to the planned garrison of 1,200 men who would operate and maintain the installation. The complexity of the underground network extended far beyond the primary gun chambers, encompassing a vast array of supporting infrastructure that would be necessary to sustain operations. Engineers carved out extensive gallery systems branching off from the main railway tunnels, creating storage areas for the massive quantities of ammunition that would be required to maintain the projected rate of fire. Living quarters, command centers, ventilation systems and electrical installations all had to be integrated into the subterranean complex, transforming the chalk hill into a self-contained military fortress capable of operating independently for extended periods. The protection of the installation from Allied attack represented one of the most critical aspects of the design, leading to the construction of reinforced concrete slabs extending 16 feet in thickness above the gun muzzles. These massive protective barriers were designed to deflect all but the most powerful bombs, while still allowing the V3 shells to emerge and begin their journey toward London. Additional defensive measures included the strategic positioning of the site inland from the coast, beyond the range of naval gunfire and far enough from obvious targets to avoid immediate detection by Allied reconnaissance. As the summer of 1943 progressed and construction crews worked around the clock to realize Hitler's vision, few could have anticipated that their monumental efforts would ultimately be rendered meaningless by a combination of technical failures and Allied determination that would prove more formidable than even the most ambitious engineering project could overcome. As construction proceeded at Mimoieques throughout the latter half of 1943, August Coenders and his team of engineers faced the monumental task of transforming their theoretical multi-charge cannon design into a functional weapon system capable of achieving the extraordinary performance specifications demanded by the Nazi leadership. The technical challenges inherent in creating a gun barrel over 130 meters in length, while maintaining the structural integrity necessary to withstand the enormous pressures generated by sequential explosive charges, proved to be far more complex than initial calculations had suggested. The engineering team discovered that the smoothbore barrel, constructed from numerous 10-foot sections, joined by 16-bolt flanges, exhibited a troubling tendency toward brittleness that significantly compromised the weapon's ability to achieve the muzzle velocities required for shells to reach their intended target. The multi-charge firing system that formed the heart of the V3 concept required unprecedented precision in timing and coordination. Each of the 32 subsidiary charges positioned along the barrel length had to be electrically detonated at precisely the correct moment as the projectile passed, creating a series of controlled explosions that would theoretically accelerate the shell to speeds exceeding 1,500 meters per second. The margin for error in this complex sequence was virtually non-existent, as premature detonation of any charge could destroy the projectile or damage the barrel, while delayed firing would fail to provide the necessary acceleration boost. German engineers struggled to develop reliable electrical firing systems capable of managing this intricate choreography of explosions while operating under the harsh conditions of an underground military installation. The projectile design presented its own unique set of engineering challenges, requiring the development of specialized 150mm finned shells capable of withstanding the extreme forces generated by the multi-charge acceleration process. These shells, officially designated as Sprenggranit 4481, weighed 97 kilograms and carried a relatively modest explosive payload of 7 to 9 kilograms, with the majority of their mass devoted to the structural reinforcement necessary to survive the violent acceleration forces they would experience during firing. The fin-stabilized design was intended to maintain projectile stability during the extended barrel transit time and provide aerodynamic control during the lengthy flight path to London, but testing revealed significant problems with accuracy and consistency that threatened to undermine the entire concept. Trials conducted at various German proving grounds throughout 1943 and early 1944 revealed fundamental flaws in the V3 design that could not be easily resolved through incremental modifications. The sectioned barrel construction, while necessary for manufacturing and transportation purposes, created weak points that limited the maximum pressures the system could safely handle, resulting in muzzle velocities significantly below the theoretical requirements for reaching London. Even more troubling, the complex timing requirements for the subsidiary charges proved extremely difficult to achieve consistently, leading to irregular shell velocities and unpredictable trajectories that would have made accurate bombardment of specific targets virtually impossible. The realization that the V3 system was failing to meet its design specifications created mounting pressure within the Nazi hierarchy, as Hitler's expectations for the weapon remained unchanged despite the accumulating evidence of technical problems. Engineers found themselves caught between the physical limitations of their design and the political impossibility of admitting failure to a leadership that had invested enormous resources and prestige in the project. Alternative approaches were considered, including shortened barrel configurations and modified projectile designs, but each potential solution seemed to create new problems while failing to address the fundamental issues that plagued the system. As 1944 dawned, and Allied bombing campaigns began to intensify their focus on German weapons development sites, the technical challenges facing the V3 project would soon be overshadowed by far more immediate threats to the entire Mimoyekes installation. The veil of secrecy that had initially shrouded the Mimoyekes project began to unravel in September 1943, when Allied reconnaissance aircraft conducting routine surveillance flights over the Pas-de-Calais region detected unusual construction activity at the seemingly innocuous Chalk Hill, 12 miles from the Channel coast. Allied photo interpreters, trained to identify patterns of enemy activity from aerial imagery, noticed the telltale signs of major excavation work, including the movement of large quantities of earth, the construction of access roads, and the presence of numerous temporary structures that suggested a significant military installation was taking shape beneath the surface. The geometric precision of the surface openings, all oriented in the same direction toward London, provided additional evidence that this was no ordinary construction project, prompting Allied intelligence agencies to classify Mimoyekes as a high-priority target requiring immediate attention. The initial Royal Air Force bombing raids against Mimoyekes began in November 1943, marking the commencement of what would become one of the most sustained and intensive air campaigns against a single target during the entire war. The first attacks, conducted by squadrons of Wellington and Halifax bombers carrying conventional high-explosive ordnance, achieved minimal physical damage to the underground installations, but served the crucial purpose of alerting German defenders that their secret project had been compromised. The psychological impact on the construction workforce was immediate and significant, as laborers who had previously worked with relative confidence in the protection afforded by their subterranean environment now found themselves constantly listening for the approaching drone of Allied aircraft engines. Throughout the winter and spring of 1943-1944, Allied bombing campaigns against Mimoyeke intensified dramatically, with British and American aircraft conducting 16 separate major raids that delivered more than 4,100 tons of explosives onto the target area. The nearby village of Landrethun-le-Nord bore the brunt of this sustained bombardment, suffering such extensive damage that it required complete reconstruction after the war. Despite the enormous quantity of ordnance expended against the site, the protective characteristics of the chalk hill and the depth of the underground installations meant that conventional bombing techniques proved largely ineffective against the V3 facilities. The massive concrete slabs protecting the gun positions, combined with more than 30 meters of solid chalk overburden, absorbed the impact of standard bombs without transmitting significant damage to the critical components of the weapon system. The persistence of the Allied bombing campaign created tremendous difficulties for the German construction effort, forcing work crews to operate under increasingly dangerous conditions while maintaining the ambitious timeline demanded by Nazi leadership. The constant threat of air attack disrupted supply lines, complicated the transportation of heavy equipment and materials, and created severe morale problems among both the forced laborers and German supervisory personnel. More significantly, the sustained bombing campaign served as compelling evidence to German engineers that Allied intelligence had accurately identified not only the location, but also the purpose of the Mimoyek's installation, suggesting that the element of surprise upon which the V3 concept depended had been irretrievably lost. The most tragic episode of the Allied campaign against Mimoyekes occurred on August 12, 1944, when Lieutenant Joseph P. Kennedy, Jr., the elder brother of future President John F. Kennedy, and his co-pilot Lieutenant Wilford J. Willey, volunteered for a revolutionary but extremely dangerous mission designated Operation Aphrodite. This ambitious program attempted to convert war-weary B-24 Liberator bombers into precision-guided flying bombs by loading them with massive quantities of explosives and directing them toward heavily defended targets through primitive remote control systems. Kennedy and Willey were tasked with piloting their explosive-laden aircraft to a predetermined point over the English Channel, where they would activate the remote control systems and parachute to safety, leaving the unmanned bomber to continue toward Mimoyekes under radio guidance from accompanying aircraft. The mission ended in tragedy when the B-24 exploded over the English countryside before the crew could escape, killing both men and demonstrating the extreme risks associated with the experimental technology that would eventually evolve into modern drone warfare. As the summer of 1944 progressed, and German defenses throughout France began to crumble under the pressure of the successful Normandy invasion, the fate of the Mimoyeke project would soon be determined by a technological breakthrough that finally provided Allied forces with the capability to penetrate even the most heavily protected underground installations. The technological breakthrough that would ultimately seal the fate of the Mimoyekes installation came in the form of a revolutionary new weapon developed by British engineer Barnes Wallis, the same brilliant mind responsible for the famous bouncing bombs used in the Dambusters raid. Wallis had been working on the concept of what he termed earthquake bombs, massive deep penetration weapons designed to create devastating shock waves through solid earth and rock, rather than relying solely on surface explosions. The result of his efforts was the Tallboy, an enormous 12,000-pound bomb measuring 21 feet in length and containing 5,500 pounds of powerful Torpex explosive, designed to be dropped from extreme altitude and achieve supersonic speeds before impact. The Tallboy represented a revolutionary advance in bombing technology, engineered to penetrate deep into the earth before detonating and creating seismic shock waves that could collapse underground structures regardless of how much protective concrete and rock surrounded them. Unlike conventional bombs that relied on surface blast effects, the Tallboy was designed to burrow deep into the target area and explode at precisely the depth where its shock waves would cause maximum structural damage to subterranean installations. The weapon required specialized aircraft capable of carrying its enormous weight to altitudes of 25,000 feet or higher, from which it could be released to achieve the terminal velocity necessary for effective Earth penetration. On July 6, 1944, 16 Royal Air Force Lancaster bombers of the elite 617 Squadron approached the Mimoyeke site at maximum altitude, each aircraft carrying a single tallboy bomb destined for the V3 installation. The precision required for this mission was extraordinary, as the effectiveness of the earthquake bombs depended not only on accurate placement, but also on the coordinated timing of multiple impacts to create overlapping shockwave patterns throughout the underground complex. The Lancaster crews, flying at the absolute ceiling of their aircraft's performance envelope, released their devastating cargo over the target area and watched as the massive bombs streaked earthward at speeds that would generate the kinetic energy necessary to penetrate the protective barriers that had previously shielded the German installation. The impact of the tallboy bombs on Mimoyekes created effects that were immediately apparent, both above and below ground, as the massive explosions generated seismic disturbances comparable to moderate earthquakes. The shockwaves propagated through the chalk formation with devastating efficiency, causing multiple gallery arches to collapse and bringing down hundreds of tons of rubble that blocked access to the gun chambers and railway tunnels. Even more critically, the explosions disrupted the carefully engineered drainage systems that had been installed to prevent flooding of the lower levels, causing water to pour into the 100-meter level and transforming much of the complex into an underground lake. The human cost of the tallboy attack was severe and immediate, as hundreds of workers who had been laboring in the deepest sections of the complex found themselves trapped by collapsed tunnels and rising water. German rescue efforts proved largely futile, as the extent of structural damage made it impossible to reach many of the entombed workers, and the continuing threat of Allied bombing discouraged sustained rescue operations. The psychological impact on surviving construction personnel was equally devastating, as it became clear that no amount of protective concrete and earth could provide security against the new generation of Allied weapons. Within weeks of the tallboy attack, German authorities made the inevitable decision to abandon the Mimoyeke project entirely, acknowledging that the combination of technical problems with the V3 design and the physical destruction of the installation made continuation of the program impossible. The remaining equipment and personnel were evacuated to other locations, while the massive underground complex was sealed and left as a monument to one of the most ambitious and ultimately futile engineering projects of the entire war. As Allied ground forces advanced across France in the weeks following the Normandy breakout, Canadian troops would arrive at Mimoyekes on September 5, 1944, to find the site completely abandoned, its guns never having fired a single shot at their intended target. Despite the catastrophic failure at Mimoyekes, the Nazi leadership's desperation in the final year of the war drove them to make one last attempt to deploy the V3 technology, albeit in a drastically reduced form that bore little resemblance to the original ambitious vision. As Allied forces consolidated their positions in France and began their inexorable advance toward the German border, military planners recognized that the original concept of bombarding London from fixed installations was no longer feasible. Instead, they turned to a more modest application of the multi-charge principle, developing shortened versions of the V3 gun that could be transported and deployed in support of conventional military operations. The modified V3 design that emerged from this desperate improvisation featured barrels approximately 50 meters in length with 12 subsidiary charging chambers, making them transportable by conventional means, while still theoretically capable of achieving ranges significantly beyond those of standard artillery pieces. These half-barrel versions were intended to provide German forces with long-range bombardment capabilities that could support major offensive operations, particularly in situations where conventional artillery proved inadequate due to range limitations or the need to engage targets protected by natural terrain features. The project came under the direct control of SS General Hans Kammler, one of the Nazi regime's most ruthless and efficient administrators, who was tasked with making the truncated V3 system operational in time to support the massive winter offensive that would become known as the Battle of the Bulge. The location selected for the deployment of these shortened V3 guns was a wooded ravine along the Ruhr River at Lampaden, approximately 13 kilometers southeast of Trier in Germany, where the terrain provided natural concealment for the installation while still allowing the weapons to be positioned for long-range bombardment missions. The two guns were carefully sited on a 34-degree slope, supported by 13 steel structures, mounted on solid wooden foundations, and oriented westward toward their designated target, the city of Luxembourg, which had been liberated by Allied forces in September 1944 and now served as an important logistical center supporting the American advance into Germany. The choice of Luxembourg as target No. 305 reflected both the practical limitations of the shortened V3 system, which lacked the range to engage more strategically significant objectives, and the symbolic importance of demonstrating German capability to strike at Allied-occupied territory. The logistical challenges of supplying ammunition for the Lamperden installation proved to be nearly as daunting as the technical problems that had plagued the weapon system throughout its development. The deteriorating condition of the German railway network, subjected to months of intensive Allied bombing, made it extremely difficult to transport the specialized projectiles and propellant charges required for V3 operations. German engineers were forced to compromise on their ammunition specifications, settling for 150mm finned projectiles with discarding sabots that weighed 95 kilograms and carried relatively modest explosive charges of 7 to 9 kilograms. The propellant system consisted of a 5-kilogram main charge supplemented by 24 subsidiary charges, providing a total propellant weight of 73 kilograms per round. The operational debut of the V3 system finally occurred on December 30, 1944, when the first Lamperden gun fired 2 warm-up rounds, followed by 5 high-explosive shells in sequence, with SS General Kammler present to witness this long-awaited demonstration of German technological achievement. The shells achieved a muzzle velocity of approximately 935 meters per second, significantly less than the theoretical performance specifications, but still sufficient to reach Luxembourg at a distance of 43 kilometers. The second gun became operational on January 11, 1945, and over the following weeks, both weapons maintained a sporadic bombardment of the Luxembourg urban area, firing a total of 183 rounds before operations ceased on February 22, 1945. The results of this extended bombardment campaign were profoundly disappointing from a military perspective, with only 44 shells confirmed to have struck within the urban area of Luxembourg, resulting in a total of 10 civilian fatalities and 35 wounded. These casualties, while tragic for the families involved, represented a negligible impact on Allied military operations and demonstrated the fundamental inadequacy of the V3 concept as a weapon of strategic significance. The approaching American forces ultimately forced the abandonment of the Lamperden site on February 15, 1945, when the first gun was dismantled and removed just as United States Army units advanced to within 3 kilometers of the installation. A second planned V3 battery at Buhl, intended to support Operation Nordwind by bombarding Belfort, was never completed before the failure of that offensive rendered the position untenable. The ultimate fate of the V3 program serves as a sobering reminder of how even the most ambitious technological projects can be rendered meaningless by the broader strategic realities of modern warfare. Following the abandonment of the Lamperden site in early 1945, all remaining V3 equipment was transported to the Röchling Works in Wetzlar, where it joined a growing collection of German wonder weapons that had promised to change the course of the war, but had instead consumed precious resources while delivering negligible military results. The specialized artillery unit designated as Artillerieabteilung 705, which had been trained specifically to operate the V3 system, was re-equipped with conventional artillery pieces and reassigned to standard military duties as the Nazi regime's collapse accelerated. The advancing Allied forces discovered the abandoned V3 components at Wetzlar and recognized immediately that they represented a fascinating example of German engineering ambition that had been constrained by fundamental physical and logistical limitations. American technical intelligence teams carefully documented the disassembled gun tubes, spare parts, and remaining ammunition before shipping the entire collection to the Aberdeen Proving Ground in Maryland for comprehensive testing and evaluation. The detailed analysis conducted by American engineers confirmed many of the technical problems that had plagued the system throughout its development, particularly the difficulties associated with achieving consistent timing of the subsidiary charges and maintaining structural integrity in the extended barrel sections. The post-war evaluation of the V3 concept revealed that even if all technical problems had been successfully resolved, the weapon system would have faced insurmountable strategic limitations that rendered it essentially obsolete before it could become operational. The fixed nature of the installations made them vulnerable to the increasingly sophisticated Allied reconnaissance and bombing capabilities, while the enormous resources required for construction and operation could have been more effectively utilized in producing conventional weapons that were desperately needed on multiple fronts. Perhaps most significantly, the extended development timeline meant that by the time any V-3 installation could have become fully operational, Allied air superiority over Western Europe was so complete that maintaining supply lines and manning such exposed positions would have been virtually impossible. The human cost of the V-3 program extended far beyond the military personnel who operated the weapons, encompassing the thousands of forced laborers who suffered and died during the construction of the Mimoyekes complex. The memorial that now stands within the museum at Mimoyekes serves as a sobering reminder of the exploitation and suffering that characterized so many Nazi construction projects, where human lives were considered expendable in pursuit of technological solutions to strategic problems. The workers who perished in the Tallboy bombing and subsequent collapse of the underground galleries became victims not only of the immediate physical violence of war, but also of a system that valued engineering ambition over human dignity. The transformation of the Mimoyekes site into a museum and historical monument represents a fitting conclusion to the story of Hitler's supergun, providing visitors with the opportunity to explore the underground galleries where one of history's most ambitious weapons projects ultimately failed to achieve its objectives. The preserved tunnels and chambers offer tangible evidence of the enormous effort that went into attempting to create a weapon that could change the course of World War II, while simultaneously demonstrating the futility of such endeavors when confronted with the practical realities of engineering, logistics, and strategic warfare. The museum's educational mission helps ensure that future generations will understand both the technical achievements and the ultimate failure of the V-3 program, serving as a permanent reminder of how technological ambition, no matter how sophisticated, cannot overcome fundamental strategic disadvantages. The final disposition of the V-3 equipment at Aberdeen Proving Ground, where it was eventually scrapped in 1948, marked the end of one of the most extraordinary chapters in the history of artillery development. The knowledge gained from studying the German multi-charge principle would influence post-war weapons development in various ways, contributing to advances in both conventional artillery and emerging missile technologies. However, the fundamental concept of using fixed ground-based installations to conduct long-range bombardments would be superseded by the development of ballistic missiles and strategic aircraft, making the V-3 approach obsolete even as theoretical engineering exercise. In the end, Hitler's supergun stands as a monument to the proposition that even the most brilliant engineering solutions cannot compensate for flawed strategic concepts and the inexorable pressures of a war that had already been lost through earlier decisions and miscalculations. Today, more than 80 years after the first excavation began at Mimoyeke, the preserved galleries beneath the French countryside continue to fascinate visitors who come to witness the physical remains of one of history's most ambitious military engineering projects. The museum that now occupies portions of the former V-3 installation serves not only as a window into the technical achievements and failures of Nazi weapons development, but also as a broader meditation on the relationship between technological capability and strategic wisdom in modern warfare. The empty gun chambers that were never destined to fire their intended salvos at London stand as silent testimony to the fundamental truth that engineering brilliance, no matter how sophisticated, cannot overcome the basic strategic realities that determine the outcome of conflicts between nations. The story of the V-3 supergun ultimately represents far more than a simple tale of technological failure. It embodies the dangerous seduction of miracle weapons and wonder technologies that promise to compensate for strategic disadvantages through engineering solutions alone. Hitler's obsession with revolutionary weapons systems that could somehow reverse Germany's deteriorating military position led to the misallocation of enormous resources that might have been more effectively employed in producing the conventional weapons and equipment that German forces desperately needed on multiple fronts. The V-3 program, like many other Nazi wonder weapons projects, consumed materials, skilled labor, and time that Germany could ill afford to waste during the critical final years of the war. Perhaps the most enduring lesson of the Mimoyek story lies in its demonstration of how even the most ambitious human endeavors can be rendered meaningless by the broader currents of history and the practical limitations imposed by physics, engineering, and strategic reality. The chalk galleries that visitors explore today serve as a permanent reminder that technological achievement must always be evaluated within the context of strategic objectives, resource constraints, and the fundamental factors that determine success or failure in human conflicts. In this sense, Hitler's supergun that never fired a shot becomes a more powerful historical lesson than any weapon that actually fulfilled its intended purpose, teaching us about the dangers of technological hubris and the importance of strategic wisdom in an age of ever-advancing military capabilities.